Hello again, my algebra friends. All right, so today we are going to discuss the differences between linear, quadratic, and exponential functions. So we did our intro to exponential functions yesterday, and I went over a little bit of this, but it's important to be able to recognize what kind of function that you are dealing with. So we're just going to take a look at each of these types of functions and how to tell them from a table, from a graph, from an equation, and from a word problem. All right, so starting with linear, which of course is the first type of function that we did this year. From a table, remember you're looking for that common difference, or if you want it, common first difference between y values. I don't know why I can't spell today, sorry. So you're like adding or subtracting the same thing every time, right? That's what a common difference is. How to tell I'm just going to go like straight down each column here. So how to tell from a table whether a function is quadratic is also a common difference, but it's a common second difference between your y values. So you do the common difference once and then you do it again. So like the first time you do it like this, like maybe you'll find like +3, +5, +7, +9. But then if you do it again, you'll find a +2, +2, +2. So that's what it means to have a common second difference, okay? And then, so again, your common first difference would be you just do it once and you find that like +1 every time, right? So that's common first difference. Okay, with exponential, you still have something in common, but it's now a common ratio between y values. And what that means, remember, is that you're multiplying or dividing, but it'll always be listed as multiplying. So it'll be listed as like multiplying a number bigger than 1 or less than 1. So you're multiplying the same thing every time. So like if you're going between y values, it'd be like times 2, times 2, times 2, times 2, like that, okay? All right, now from a graph. Graph is the easiest, as long as you're given a whole graph to look at. Might as well take advantage of the fact that I have different colors, right? So if I look at a linear function from a graph, well, what does it look like? It looks like a line. Look at that, linear. If I look at a quadratic, it's that parabola shape, that U shape that we talked about. And then an exponential function, remember, it can be either growth or decay, but I'll draw growth just because that's kind of the more common one that you'll see. But it starts off kind of flat or flat looking, and then it jumps up really fast. So you will find like a line, you'll have some symmetry here across a line or two. And then here, you'll probably have some symmetry. Oh my gosh, symmetry, right? Over the axis of symmetry. But exponential functions, there is not symmetry too. So they look very, very different on the left and the right. All right, and then linear from an equation. In equations, we're going to look at parent functions. So y equals x, or y equals mx plus b, or ax plus by equals c, or any of those. But the big thing is that x has a degree of 1. And remember, degree is the highest exponent that you have, right? So like if you have x to the third plus x, there is an x with an exponent of 1, but it's not the degree. The degree is 3. For quadratic, your parent function is y equals x squared. We also know it as y equals ax squared plus bx plus c. But what matters here is that x has a degree of 2. And then exponential is super easy to tell. You don't have to look for a degree. It's, remember, y equals a times b to the x. And what you're really looking for is that x is in your exponent. So it's not a base like this, like a base of 2 or a base with 1 as your exponent, but the x actually in the exponent, hence the term exponential function, right? All right, and then from a word problem, word problems, remember, you usually have to go a little bit further and like turn it into a table or make an equation out of it or something. But there are some hints sometimes that you'll get from word problems. And for linears, it's word like constant, or you'll hear like rate of change in it, or, increase or decrease. I mean, that can be in a lot of them, but oftentimes these will be like, I say that the t-shirts, right? So your setup cost and then, the same cost per. So we put like cost per blah, 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 right? Goes up or down by the same amount every time. Quadratic functions in word problems, we got to these like right before we left, so I don't even know if you remember them or not. But these are the ones, they're like the projectile motion ones or the height functions. So where it's like, the negative 16 x squared plus the initial velocity times x plus the initial height. I believe the example, if you remember it, was the one that was you're comparing like a, little league baseball player and some guy like throwing a football off of a building or something like that. So that's what you typically see with quadratic functions. Exponential, you're going to look for words like doubles, triples, like half-life problems are exponential problems, interest problems, like not, oh, I'm so interested, but like bank interest, right? So simple or compound interest, depreciation or appreciation. Again, not like I appreciate you, but appreciate meaning like to grow in value. So there's a lot of money problems and a lot of value problems like that. Population problems are usually exponential. So that's how you tell for each of these. So if we just turn to the back, this is a pretty quick lesson for today. So this is your optional assignment. And you can see it's linear, quadratic, and exponential models. So it'll say which kind of model best describes. Well, that's linear, quadratic, or exponential. That's what they're asking. So when on number 1, you're going to graph. So you have -2, 0, -1, -3, 0, -4, 1, -3, and 2, 0. And of course, you're going to want to connect those. And if you do, you'll look at that and say, well, that looks awful lot like a parabola, which is quadratic. So that's how you do 1 and 2. 3 through 7, you are going to look at the differences in the y values. Okay, so again, remember, you always, and for sure have to make sure that the x value is going up by the same amount every time. So -5, -4, -3, -2, that's great, going up by 1. So 9 to 0, and then 0 to -7, and then -7 to -12. So 9 to 0, so I have a -9, and then 0 to -7, I have a -7, -7 to -12, I have a -5. So it's certainly not linear, right? To go from 9 to 0, I'd be multiplying by 0. So it's not exponential. So what I'm going to want to do again is maybe look for a second difference. So -9 to -7 is a difference of +2. And then -7 to -5 is a difference of +2. So that is quadratic because you have a common second difference. Okay, so just look at your differences in your y values. And I believe, let me just look real quick, all of these are good with your x values. They're going up by the same thing every time. Be careful. In number 6, it goes up by 2s for your x's. Same thing with number 7. All right. Number 8, use the data in the table to describe how the restaurant sales are changing. Then write a function that models the data. Use your prediction to predict the amount of sales after 8 years. Okay, so let's see. So this is going, if I look at this real quick, this is going, first of all, down by 1,000 and then down by 50. Okay, so it's not linear. All right. And then what I'm going to want to do, I'm going to want to see what the difference is, just for fun, between 18,050 and 17,147.50. Okay. So that's a difference of, I'm sorry, hold on a second. I was just looking at the the zeros and the 50s. Give me a second. Sorry, that would be 950 is what I meant. And then this goes down by 902.50. So there's not a common difference here, right? And then there's also not a common difference here because this would be 50 and then that would not be 50. So what you're going to want to do is you're going to want to, like, this is kind of weird when you're making exponential functions because you can just see like, well, it's not linear and it's not quadratic, so it must be exponential if it is any. So you're going to want to take you want to divide in order here. So you want to take 20,000, divide it by 19,000. Okay, and when you do that, you get 1.05. And then if you do 18, yeah, I'm telling you to divide that way, and you probably shouldn't, even though it'll make a lot more sense. Makes a lot more sense to do it this way, but we're gonna have to write it the other way. So let's divide this way. I'm sorry, I'm probably confusing you more than anything else. So we're gonna divide right to left, because when you write it, you're gonna have to write it as a multiplier, not a divisor. And so I don't want to confuse you. So we're gonna take 17,147.50. Divide that by 18,050. And I got 0.95. Okay, so when I divide this by this, I get 0.95. And then what I'm going to do is see if I can get the same thing. So 18,050 divided by 19,000. And I also get 0.95. And then I get 19,000 divided by 20,000. And I also get 0.95. So what happens is, and the reason why I divided that way is because it's a lot easier to take the right divided by the left in numbers like this than it is to see, okay, well, what do I have to multiply 18,050 by to get to 17,147.50? Like, you wouldn't know that off the top of your head. If this was like, 2, 4, 8, 16, then it's clear, right? But it's not clear here. And so when it's not clear, you want to take the right numbers and divide them by the left numbers. And if you get the same thing every time, then that's your common ratio. So your common ratio is 0.95, okay? And then you need your starting point too, right? Because from yesterday, remember, it's y equals a times b to the x, where a is your starting point. Your starting point, remember, is where x equals 0, and b is your common ratio. So my starting point is where x equals 0. Where x equals 0, y is 20,000. So my function is y equals, I'm just doing that to separate, sorry, 20,000 times 0.95 to the x. So that's my function. And that says use my function to predict the amount of sales after 8 years. So I plug 8 in for x. So y equals 20,000 times 0.95 to the 8. Where you can see it. Times 9.5 to the 8th. And that is approximately, this is dollar values? Yes, okay, $13,268.41. So, and of course, since you're talking money, you want to round it to the nearest hundredth. So there you go. That, my friends, is telling linear, quadratic, exponential, and then of course it's just a little bit more as you go. Now this one's quite a bit easier. Number 9. So let's do the easy one to do there. All right. If you have any questions, you know where to find me and when. So that is it for today's lesson. And let me stop this guy here.